the title first. Okay, so I will begin. Thank you once again for the opportunity to speak here. And the title of my talk is Integral Points and Curves on Moduli of Local Systems. And maybe I would like to first begin by motivating the types of varieties or algebraic varieties that I'll be studying. And let me start with the following definition from complex algebraic geometry. We say that an irreducible algebraic variety V is log-Calabi-Yau if it has a nice compactification with certain properties, if there exists a normal projective variety Z and a reduced effective divisor D inside Z, such that this V is the open complement of D inside Z. The crucial property that we want is that the canonical divisor of Z we take plus D, the class of divisor at infinity, is trivial. Now, rather than trying to explain, this is all over just complex numbers, sure. Just rather than trying to explain in detail what this means, I want to give some examples of these varieties. And from the examples, it will become clear that somehow a lot of the varieties that are central to number theory and Diophantine geometry are of this type. So in dimension 1, these are the multiplicative group and elliptic curves. And just in higher dimensions, the generalization of GM is algebraic tori, and also elliptic curves and more general abelian varieties. And K3 surfaces. So a lot of the varieties that were mentioned in the number theory talk yesterday and also in the other seminar talks today were of this family. And also another family comes from generic hypersurfaces of degree D equal to n in affine n space. And here I note that from the Diophantine point of view, if we look at affine hypersurfaces inside affine n space, then if D were bigger than n, then this is the regime where we have conjectures like the Lang-Voita conjecture that would imply that the integral points on V will be sparse. Whereas if D was less than n, then we have, for example, in certain cases, the circle method and related analytic techniques, and also some Manin or Batyrov-Manin type conjectures would predict that there are many integral points on a variety, on a hypersurface when D is less than n. So just can be seen from this example, we see that this log-Calabi-Yau condition is really somehow the boundary case where the global geometry of the variety itself doesn't automatically give you a prediction of the behavior of the integral points. And in other words, this means that the behavior of the integral points will be more interesting when some structure is present. So the theme that I'm pursuing in my work and to many extent the earlier talks today is that for V log-Calabi-Yau, one goal might be to understand the structure of the integral points. And I should mention that here I didn't assume that V was, I can allow V to be projective, in which case Z is equal to V, and then D is the zero divisor. And this condition is just the triviality of the canonical divisor, which includes the examples of abelian varieties and K3 surfaces. So here, we take this to be the rational points if V is projective. We want to understand the integral points in the presence of certain dynamics, loosely speaking. And in this spirit, I want to give the canonical linear examples for tori and abelian varieties. For example, we have the Dirichlet unit theorem. For tori, and the Mordell-Weil theorem for the group of rational points on abelian varieties, where some sort of finite generation result holds, and these are very useful, of course, elsewhere in number theory. And in this talk, I want to discuss an example of log-Calabi-Yau varieties for which we want to pursue this type of understanding, but where the underlying dynamics will be nonlinear in nature. So I want to introduce the objects. And these are objects arising from topology. These will be moduli space of local systems on surfaces. So let sigma be a compact oriented surface of type Gn. By this I mean that the surface has genus G and has n boundary components. And I will label the boundary components of the surface C1 up to Cn. And in this talk, I will assume that there's at least one boundary component and that this inequality is satisfied. In particular, the surface is negatively curved. And I'll denote by X just a moduli space of local systems, SO2 local systems on my surface. So here, this is an algebraic variety whose complex points parameterize the semi-simple SO2C representations of the fundamental group of the surface. And the varieties that I'm really interested in are subvarieties of X, which are given by the following condition. I'm parameterizing those representations such that the trace of the representation along the boundary curves, Ci here, these traces are fixed. And we'll be interested in looking at fixing the traces to be integral. So for each n tuple of integers n, and for each sigma surface as above, we have this variety xk. It turns out this is an affine irreducible variety of dimension 6g plus 2n minus 6, which is positive by this assumption. Okay? So these are in general very large. These are a large family of varieties. And how does this talk relate to the previous talks in this sequence today? Well, it turns out that when we take G and N to be 1, so I have a sigma is a one-hole torus. So if we picture the surface like this, I have two curves, simple closed curves, which generates freely the fundamental group of my surface. Then it turns out that if I take the sequence of regular functions on my moduli space X, trace along A, trace along B, and trace along A times B, then this is a regular function mapping into the affine 3 space, the three functions. It turns out that this is an isomorphism by classical work of Fricke and Klein. And each of these xk's that I'm interested in are given under the identification of the variables x, y, z by the equation x squared plus y squared plus z squared.
Yeah, I don't know that everybody gets.
Yes.
This character variety, so you look at all this group is looking at fundamental groups basically free.
Right.
So
Yes.
you're looking at all representations of the fundamental group into SL2. So that means just take the generators to any matrices, that'll give you all the representation. The tricky thing is divided is to this double slash there,
Yes.
where you divide by inner conjugation, so simultaneous action by conjugation. And then these varieties have this interpretation of these representations, but they also can be realized in terms of equations.
Right.
They represent
Yes. Yes. Yes.
They affine varieties, and they defined over Z.
Yes. For if I choose this k to be z, a tuple of integers, then all of these have sort of natural integral models defined over z. So they have, a priori, they have integral polynomial equations defining them. And in this case, the equation is given by this. And you might remember this from Professor Gambert's talk, where he talked about this Frickett-Klein relation of the trace of the commutator in terms of the traces of other elements. So that's where it arises. And here, and I should mention that in the general case, we have the mapping class group, which is just a group of isotopy classes of orientation preserving diffeomorphisms of my surface, fixing the boundary pointwise. And this naturally acts by pullback of local systems on each xk. And in the case of Markov surface here, this gamma action essentially recovers Markov descent. Or Markov moves. And I should note that this transformation preserves the integral structure of these varieties. So in particular, it acts on the integral points. Okay?
By the way, now that you've seen so much about Markov-Hurwitz, is the Markov-Hurwitz a moduli of any? I mean, Hurwitz a moduli?
No, I don't know any interpretation of that kind. It would be very interesting, but
I mean, they're log-Calabi-Yau.
Yes, right. Essentially from this example, generic hypersurface of degree.
Now, does the log-Calabi-Yau as an affine condition about a compactification?
Right, yes. For affine varieties, log-Calabi-Yau is really about how you compactify it. And I should note that, what was I going to say? So I should note that here, from this explicit presentation of my variety, in the case of Gn equal to 1, 1, we get essentially a Markov surface. So we see that already by this example that these varieties are log-Calabi-Yau. And so the natural question to ask, and which is theorem 0, is that are these log-Calabi-Yau? And it's true that for general sigma and general k, we see that we can show that every one of these varieties is log-Calabi-Yau. So we have these very large, infinitely many families of log-Calabi-Yau varieties endowed with this naturally nonlinear action of the mapping class groups of surfaces on these integral points. And so this provides a motivation for pursuing the kind of Markov descent further into this setting. But I should note that here, in general, these varieties, they don't, I mean, there are relatively few examples where the explicit equations are known, and regardless, the equations will likely be very complicated as I increase the complexity of sigma. So the explicit approach might not be the best to choose. So in any case,
This is one of my main interests, is to understand these varieties which are at the threshold where they don't fit into any theory that we have, or even any conjectures about integer points on such varieties, of which the Markov, to me that's what's interesting about
Right,
Yeah,
right.
we have a whole slew. They all have the same properties, same action, same conjectures probably.
Yes.
And they give us a family of varieties, which a rich family, by which we can try to make proper conjectures. We don't have good examples.
Right.
Many varieties in elliptic curves and projective spaces are too simple. All right.
Sure, yes. Right, so we somehow want to look for other examples besides the more classically studied ones. And are there any questions about the first section, by the way? No. Okay, so
when
yes.
When you have a log-Calabi, I mean, that's a condition over C.
Yeah, it's a complex.
Sure, yeah, it's a complex.
And
Yeah.
you have to choose an integral model.
Right, yes, yes, yes.
The idea is that shouldn't depend on the choice of B.
No, it shouldn't matter what ground field you live in. It's a geometric property. It's a global geometric property of the variety that you're working with. It's just like how, if you're looking at
Two or higher, you have only five.
right, if you're looking at algebraic curves and somehow the genus or the Euler characteristic of the Riemann surface dictates how the integral points on the surface on the curve behaves, right? It's kind of like that. Yeah. Okay, so I want to talk about descent. And just like in the Markov or Markov-Hurwitz cases, in general, it'll be that there are some these exceptional or parametric solutions that appear in moduli spaces. So I want to account for that as well. But in the end, I will still want to arrive at some sort of finite generation statement akin to, say, there's a unit theorem or Moduli theorem. So I want to make, for this reason, the following definitions, and these are somehow natural definitions from the moduli theoretic interpretation of these spaces. So first, I want to single out the so-called non-degenerate integral points on xk to be those representations. By the way, the integral points here just means that this rho, the local system or the representation, has integral character. So the meaning of integral is quite natural here. So I want to look at such representations such that the trace of rho along any curve A is not equal to plus or minus 2, where A runs over simple closed curves in size sigma, which are non-contractible and also not isotopic to any of the boundary components. And this I call essential, or this is called essential. So essential curves. So this is a condition that I put on. And to account for the complement, I will define an algebraic variety. V is parabolic if it is covered by images of non-constant maps from the affine line to the variety. So in general, the parametric solutions that we'll find will be of higher dimensions in these varieties. So I adopt this.
That's kind of complex then.
Yes, it's over C. Yes. Okay, so with these notations, I can state the first theorem regarding the descent on the integral points of these moduli spaces. So the first result is that I look at the action of the mapping class group on the non-degenerate integral points, and this is finite. And this statement is for all k, and there exist proper parabolic subvarieties V1 up to VR inside xk, such that the complement, if I look at the complement here, so the degenerate solutions, so to speak, then these lie in the finite union of orbits of the sets of integral points in these parabolic subvarieties. So this second part is a sort of a generalized finiteness statement in the presence of lots of affine lines, etc., which make the matter complicated.
I assume that the set can be empty, right?
Right, a priori can be empty, yes, yes. I mean, this VI Z can be empty, yes.
That's not being discussed yet. That's generalized other things. This is just generalizing the descent.
Yes. Well, I want to say.
Yeah, I think you should say a word about the proof because it's so different to any of these descents that we've seen today.
Okay, yes, I was going to state the key ideas in the proof, or the key geometric setup that is needed for this.
We saw a number of different height functions and then even descent for the Markov and the log-Calabi-Yau and all this stuff. But yeah, the simplistic viewpoint is, you don't have the equations.
Right.
You got to think of the space as what the objects really are. By the way, in the theory of modular curves, it's very similar. Nobody writes down the modular equation for x naught n except Elkies. and he has to use a computer. You use the interpretation, it's the moduli space of something else, and then that's how you study it. It is representable.
Right.
And he's never going to write the equations down, but he'll still prove theorems down, right? So this is the abstract way.
Right, so the modular interpretation will be key in what follows. So the geometric setup is the following. So I suppose that A1 up to A3G plus n minus 3, these are mutually disjoint and non-isotopic essential curves on my surface, also called a pan-stick composition of my surface. Yes, I was just going to. So for example, if I have a genus 2 surface with one hole, then an example of a pan-stick composition might be a collection of essential curves like this. We see that if I cut out the surface along these curves, then each component is a pair of pans. That's why it's called a pan-stick composition. Then associated to a pan-stick composition, I have the sequence of regular functions. So trace of A1 up to trace of A3G plus n minus 1, n minus 3, from my moduli space, which I fixed, xk, down to A to the 3G plus n minus 3. And this is, in many ways, an integrable system, which I won't go into detail, but the structure is quite reminiscent of the usual picture of integrable systems in Hamiltonian dynamics. And the idea is that the fibers, the generic fibers, are algebraic tori with action akin to Hamiltonian flow of 3G plus n minus 3 copies of Z. By the way, this is half the dimension of xk, so the algebraic tori in general will be tori of half the dimension of xk. And this action given by products of what are called Dane twist. I'll say in a moment what this is. And these are elements inside the mapping class group which pairwise commute. And these are Dane twists along the 3G plus n minus 3 disjoint curves. And such products I'll refer to as multi-twists for later on. And what is a Dane twist? A Dane twist inside the mapping class group is a diffeomorphism that is given by, say, taking one of the curves A1, say, and I cut the surface along that curve. I rotate one of the ends 360 degrees and glue them back together. That defines the diffeomorphism of the original surface. And so by the usual action of gamma on the xk defines the action on the, we have this action. And it turns out that when these curves are disjoint, these Dane-twist actions commute. And so we get an action of this, these multi-twists on these fiber tori. I should mention that in general, these fibers can be more degenerate than just simple algebraic tori, so there is more involved than just this picture, but for expositional purposes, this is sufficient, I think. So this picture already suggests that we reduce the descent of integral points on xk into two steps. Namely, first, we want to reduce, in this Hamiltonian language, the action variables, which is just to say that I want to, given a rho inside xk of z, I want to choose a Pence decomposition such that these tuple of traces is bounded in an a priori compact set. And what this amounts to is to show a uniform bound on what may be called the systolic trace of a local system. So this is just the infimum of the traces of rho in absolute value for over all essential curves in my surface. Essentially, this first step reduces to this.
So,
yes.
you give a bound for this systolic trace, where you call it.
Yes.
This the way you get different essential curves with the mapping class group, so this is where you're doing the descent
Yes.
of moving around with your Markov moves. If this is applied to Markov in particular,
Yes.
that's secretly in that statement that inf is bounded, you really
Right.
produced an essential curve, and the essential curve
Yes, I use
producing from your starting curve is some action by the Markov group.
yes, this.
The groups called the mapping class.
Yes, that is precisely the idea. And I should mention that what is sort of crucial behind this picture is the fact that the mapping class group acts naturally on the set of isolopy classes of essential curves on my surface, and it's intuitively clear that this, the set of orbits of this action is finite. So that is essential in this, making this kind of argument. So in any case, one reduces to this statement, and this is in many ways similar to Berge's theorem about bounding the shortest, the length of bounding, getting an upper bound, uniform upper bound on the shortest geodesic on a hyperbolic surface with prescribed, say, geodesic boundary components. And it's just, this statement is just generalizing this Berge's theorem to the case of all arbitrary SO2.
I'm talking the actual Markov case.
Yes.
The case 0 is Teichmuller, is the Teichmuller component.
Yes.
Berge's theorem
Yes.
will give you Markov's descent.
Yes, that is
Using
true.
this
Yes.
hyperbolic geometry, correct.
Yes, that's
But,
true.
He's proving this for any K.
Yes, for any surface and any K. And also, I should mention that I do this not just for integral points, but for all the complex points of K. So this is for some choice of K, this will contain the so-called Teichmuller component consisting of hyperbolic structures, but it's more general than that. And because of time, I won't go into detail, but the two ingredients that are used are harmonic maps and sort of systolic geometry. And maybe if I have some time later, I'll come back to this, but I'll leave this here for now. Yes. Well, this is the first part, and then the second part as you might expect, is that once I reduce the action variables or the variables downstairs, then I just have to do the descent on the fiber tori using the multi-twist. And you can imagine that is much more straightforward. So just to complete the sentence, reduce the so-called angle variables on the fiber tori using multi-twist. And I would just like to remark that in fact, one can notice that the arguments that are used in the descent here allow you to generalize this sort of finite generation to prove an analogous result for all of the imaginary quadratic integral points on K. So K, imaginary quadratic, and OK is a ring of integers. And here I again put some non-degeneracy condition. It is slightly different from the integral case, but a result similar in spirit holds for the union of all imaginary quadratic points. Namely, some finite generation result holds.
In Markov, that was in the Markov case, this is what Silverman looked at, about dimensional quadratic field, and still got this finiteness over all of them. Very special thing.
Yes, right. So,
This is completely
right, this is not a new observation, I would say.
this generality.
All right, in this generality is a new result, but for Markov surfaces, this type of finiteness over all imaginary quadratics was already observed. And now I want to, in the last few, sorry, how long do I have? Until I have 10 minutes or 12 minutes?
By the way,
Okay.
in part
Yes.
one, you're not using the Dern twist, right?
In part one?
Yeah.
No, so here, I mean, implicitly I'm using the whole mapping class group action, but what I'm doing is essentially just this theory of harmonic maps and I'm using differential geometry arguments, so basically.
I mean, one thing I think you should point out right now, which is
Yes.
really observed in Silverman and Baragar, is that this finiteness is only over Z and imaginary quadratic rings, and fails. It's not the usual algebra geometric setting where if we look at an integer
Right.
and a number field, everything fails all of a sudden because this group doesn't change. The group,
Yes,
the
right.
automorphism group of these varieties is fixed. It doesn't know about the base.
Yes, that's true. Right, so the discreteness in C is crucial in this argument here. But on the flip side of it, I should mention also that somehow the mapping class groups, somehow in the linear arithmetic group case, there is a sort of a clear idea that somehow one should get this finiteness based on the fact that there's arithmetic involved, I guess. But somehow the definition of the mapping class groups do not involve anything to do with, a priori, anything to do with integers. So the fact that one should get this, some sort of finiteness resembling, right, yeah. So anyways, that's kind of, but I want to now turn to some new results that continue from this finite descent result and applying the philosophy behind descent to the study of algebraic curves in these moduli spaces and their integral points and some other work as well. So I should mention that already I drew the parallel between this finite generation and, say, Dirichlet's unit theorem and Mordell-Weil theorem. And one of the motivations for proving Mordell-Weil theorem, if I recall correctly, was to prove, to show that, say, an algebraic curve of genus 2 or higher embeds into its Jacobian, and using the finite generation of the rational points on the Jacobian to deduce some finiteness results, say, prove Mordell's conjecture about the finiteness of rational points, or even, say, Ziegel's theorem about the finiteness of integral points on these curves.
History is not as you say, but
Oh, okay.
Completely screwed up.
Okay. Well, I would say that will be one way to motivate. But anyway, so this begs the question, maybe I can use this finite generation result to say something about curves embedded inside here. Maybe I can go slightly beyond 0 and to show that maybe there are only finitely many imaginary quadratic integral points over all such fields K as soon as a curve is sufficiently general. And this theorem is something towards that. So let C be an algebraic curve. Let's say that it's irreducible, and I'll put the condition here non-degenerate. I'll come back to this later. Curve defined over Z. So it's defined by some polynomial equations inside xk over Z. And then one of the following holds. So it could be that if I take the union of all integral points over all quadratic imaginary integers, then viewing this inside the complex points is finite. Or, well, it could be that there are infinitely many such integral points on C, and then there I have a dynamical sort of a justification or explanation for why it might have infinitely many points. So if this is infinite, then C is invariant under a non-trivial gamma inside the mapping class group. Now, if a curve is invariant under the multi-twist, one can imagine that given
A multi-twist which is infinite order.
Well, that's something that I sort of put under the rug,
Why
but
is it not so interesting?
well, yeah, I mean multi-twist, infinite order, yes.
You want it to be infinite order.
Yes, it's just that, well, somehow it could act on the points here with finite order, but it itself as a group inside gamma, it will be infinite, yes. And I should mention that if I have a curve which is invariant under a multi-twist, and it's somehow intuitively clear that if I have one integral point on C, I should be able to create many integral points just by taking this multi-twist, yes. So this gives you a reasonable result. I should also add that, in addition, in both cases, this set of quadratic imaginary integral points can be effectively determined.
This gamma is invertible, so it will act on this curve as an automorphism.
Yes, yes.
So then the genus of the curve must be 0
Yes, it essentially has to be like a torus.
or a torus.
Yeah, yes. Yeah.
So if the curve is higher genus,
Right.
to start off with, that's not an issue.
Yes. So I should say something about effectivity. I should note that Ziegel's theorem in general is not known to be effective. The Ziegel's theorem says that if I have a curve of negative Euler characteristic, then it should have only finitely many integral points. Here I have effectivity and also have not just finitely many integral points over a fixed field, but over all imaginary quadratic fields. So that's an interesting
I think
feature.
That's the more interesting part, because many cases of Ziegel's theorem are effective, and you don't know what, you haven't told us what kind of curve you're getting here.
Well,
So the issue of having a curve which has only finitely many points over the union of all imaginary quadratic fields
Yes.
is not very interesting. So
Um,
using the full force of
I see.
I'm not saying that, but
Yes.
if you write the curve down and you went
Yes.
to this guy here on Connell, he'll probably make it correct.
Oh, but I,
In other words, the fact that it's not known for every curve
yes.
is one thing, but for there are a lot of effective results.
Right, that is true. So I should be more careful in comparing with the, yes.
Unless you gave us an example that Baker can't show is effective.
Well, I mean, I do have some hyperelliptic curves, but maybe I should save it for later. Yeah. So I want to say one simple corollary of this, going back to the Markov surface case. So in the case when xk is a Markov surface, well, this shows that every Diophantine equation f of x, y, z equal to 0, where f is a polynomial in 3 variables in x, y, z, on the surface with this relation can be effectively solved over, say, over z, over O of k as well. But so I pick any polynomial equation with integral coefficients. Then, in principle, I can compute, I can solve this equation as an equation on the surface, Markov surface xk for any choice of k effectively, meaning that either is finitely many or there is I can enumerate the all the solutions by this method. Okay, so that is one corollary of it. And I should also mention that this also generalizes.
I think
Yes.
I wouldn't be surprised if somebody could prove the effectivity, because this is now a curve, and the issue is
Yes.
whether this is one of these curves which
Yes.
you can prove effective. But the fact that that's true over O of the union,
Yes.
and that must use this descent. That's so I think that's the.
Okay. Yes. And I should mention that in a similar vein, there's this result of a long and read having to do with sort of character curves arising from hyperbolic 3 manifolds with one end, one cusp, and they show that these curves, which arise as irreducible components of the character variety of the manifold, they have similar finiteness property like this. And in their proof, essentially using the embedding of the cuspidal torus into the 3 manifold, they map it into the Cayley cubic essentially here. And I should say that the argument here sort of generalizes that and recovers their result essentially. I want to say, using the last 2 minutes I have to say another thing, which I think is quite also interesting. And by the way, I should mention that what the method of proof of this theorem is somewhat similar in spirit to the descent for the theorem 1. Essentially, there are 2 ingredients involved. The first ingredient is a non-Archimedean analog of the boundedness of systolic traces like this, where instead of C with its absolute value, I essentially consider the function field of the curve with the absolute value coming from a point at infinity of a compactification for C. This is not unlike the degree argument for finding parametric solutions on these curves. So with that, and also the second ingredient I should say is that this works to prove this theorem when C does not lie in any of these fiber tori that I discussed here. If C does lie in a fiber torus, then I use a Baker's theorem. And it turns out that Baker's theorem can be used quite easily.
You are using it someplace.
Okay. to
You're going to lose. You won't get this Diophantine of the imaginary quadratic.
Oh, I still get that actually.
Sure.
Yes, because it's hard. Yeah.
There's a theorem where once D is large and not points at all.
No. It's just what happens is that using the descent as in step 2 here, I take all the curves down to a finite set. I just take one point and take the orbits of that and compare that with the equation. Yes, I can. Yes. Anyway, so the theorem 2, I'll quickly end with this, is that I want to look at the point. So the theorem is that there exists a proper closed subset, proper closed algebraic subset, such that every non-constant morphism from A1 to xk is gamma equivalent to some map from A1 into this proper closed subset. So up to mapping classical equivalence, we have this sort of generalized finiteness statement for maps from A1 into our moduli spaces. And this is somehow reminiscent of the result of Stirk, where he shows that the set of orbits of the automorphism group of a K3 surface acting on the set of smooth rational curve classes on the surface is finite. And somehow this doesn't go that far. It's just saying that there's some sort of a generalized finiteness statement here. So, and this is also, I think, is an interesting application of the philosophy of descent here. So I went over time. Thank you.